Hello, Mr. Moa. Welcome to our grade 12 chemistry ISU. Lexi, Kate, and I are going to be in this group, but unfortunately the others could not join us because although we've run several practices today at Lexi's house, Lexi could not come home with me because she was grounded and Kate has school tomorrow. And so because the other rounds did not work and our previous experiment that we wanted to do was unsuccessful, we came up with a plan for a new experiment and we tried it out once, and then here I am doing the final test run for you today. We do have the videos if you are interested in just double checking that. So first what I'm going to be doing today is a little bit of an introduction. I'm just going to state exactly what the reaction is. Then I'm going to go into the ingredients. Then I'm going to talk about the safety, everything that we're beginning with. And then I'm going to take a quick pause, and then we're going to start out with the procedure. We're going to go and we're actually going to effectuate this, and I'm going to tell you a little bit about what is happening. So to begin today, what we're going to be doing is a reaction between citric acid and sodium bicarbonate. So this reaction will be completed with the following ingredients of 100 milliliters of water, which we have measured and in this wonderful cup. Then we're going to be using 1 teaspoon of citric acid in this plastic bag, which is sealed. 1 spoon of sodium bicarbonate, which is in this sealed plastic bag. 1 thermometer, which I do have right here. And 2 teaspoons, which I have right here. So we also have 1 coffee cup calorimeter. So the transfer of energy, so to go more in depth into the coffee cup calorimeter, so the transfers of energy that occur during a chemical and physical changes can be measured through a process called calorimetry, which we're going to be not necessarily effectuating today, but I'm going to be showing you a reaction that you can use next to actually do all the mathematics. So a calorimeter is actually a device that measures the energy changes associated with these physical and chemical changes that are happening. So we have 3 parts to our coffee cup calorimeter. I'm just going to bring you a little closer and so you can see. So I'm just moving everything around a little bit because I want to give you optimal view. So number 1, we have our well-insulated chamber. So this is what I'm just going to take this off right here. This is our styrofoam cup. We are going to be using 2 styrofoam cups, and what these are going to do is they're going to prevent the energy loss. Then we have a tight fitting cover. What I'm going to be doing is I'm going to be having this cardboard cover right here that fits onto the cup. This is going to prevent any heat loss. This has a hole in it for the thermometer, and as I don't have a glass stirring rod, which are usually used, as my stirring mechanism, I'm going to be swirling in the cup. So changes in thermal energies are added as water temperature changes. So this process is useful, but it's not necessarily perfect. And if you want a perfect example or better calculations, what you want to do is you want to use a bomb calorimeter or something like that that will give you better results and more accurate results. Because although these are good, there is going to be a loss of energy. And it's just going to eventually escape because this isn't perfectly sealed. As you can see, even though I have this on, it's not going to be 100%. So next I'm going to talk about our assumptions real quick. I'm going to put you back now that you've accurately observed our coffee cup calorimeter with the thermometer going in here. And you are currently in a makeshift Cliff Bar holder, which I do find to be quite enjoyable. It's fun making that. Our assumptions today with this whole calorimetry is that any thermal energy transfer from the calorimeter to the outside environment is negligible. Any thermal energy absorbed by the calorimeter itself is negligible, and all dilute aqueous solutions have the same density and specific heat capacity as water. And this is only valid if they take place in a diluted aqueous solution or in water itself. And this will be taking place in water. So we're good. Next, let's real quick talk about safety. I don't have any safety goggles on me as all of the ingredients are put away and they aren't sealed. Don't worry, I made sure of that. My hair is tied back just because that's proper lab etiquette, even though I'm not going to be using any heat or flames in this experiment. It's good to keep it out of my face just so I can see what I'm doing 100%. Then I'm going to be telling you about the MSDS sheets and what I'm going to be doing to prevent these horrible things from happening to me. So the sodium bicarbonate, SDS, states that it's slightly hazardous in case of skin contact, eye contact, ingestion, and inhalation. So what's going to be happening is in this experiment, CO2 is going to be produced as a byproduct, which I'll get into later in the procedure. But what I'm going to do is when the bubbles are forming in this experiment, I'm just going to take a step back because they are going to be releasing CO2, and that is going to be quite dangerous. That's going to protect my respiratory tract, and I have cleared the dog out because CO2 floats closer to the ground. Shout out to Nicola for telling us that. And so she is safely in her cage, very far away, in order to prevent any medical problems for Opal over there. I also have safety goggles right here from Nicola once more, thank you, that I will be using to protect the eyes. And to protect the majority of the skin, I have a long sleeve and longer shirt on, as well as I have made a makeshift lab coat of this cardigan that is on backwards in order to cover more of my chest area, which would otherwise be exposed as it goes quite high, and the sleeves are quite long due to the fact that I have both on. I am wearing my feet are covered, but I'm not necessarily going to be using any acids that could be ultra corrosive to my skin, so I don't have to worry too much about that, but it's always good to keep it in your mind. Next, let's talk about citric acid. So citric acid is hazardous, not slightly hazardous like sodium bicarbonate, but it is hazardous in case of eye contact, inhalation, and it's slightly hazardous in case of skin contact and ingestion. So all of those, I'm going to be using the exact same protocols as I'm using for sodium bicarbonate. So I have my goggles, I have my makeshift lab robe, which is keeping me safe. So it could also, severe overexposure to citric acid could also lead to lung damage and even, in worst case scenario, death. There's also some choking involved there, which I'd like to avoid very much because summer just started. So that is what I have so far for part one. Next, you're gonna see me starting to get into the experiment. Hello, Mr. Amoa. I am back with some goggles on because after I explain what's gonna happen, I just wanna jump straight in. So, first of all, what occurs? I have my little cue notes with me. So, sodium and bicarbonate, they're gonna separate from one another. And then the bicarbonate is going to then react with the citric acid. This creates an unstable compound called carbonic acid. And this carbonic acid is so unstable that it's going to fall apart and create water and carbon dioxide, which actually cause bubbles. These bubbles are going to be observed as a product in this reaction, and they are going to be releasing CO2. So this solution, how does it tie into the unit? So although we do have our coffee cup calorimeter, it also ties into endothermic and exothermic reactions naturally due to the calorimeter. So this is actually a endothermic reaction. It creates a drop in temperature because it is drawing in energy from its environment in order to break bonds, which takes energy, and then it may have an increase in temperature when it forms bonds because that releases energy. So this means that the products are going to be higher energy than the reactants. So let us go straight in with the procedure. So I have everything on. We got to do a quick double check that we are safe. So number one, let me begin by pouring in the H2O. This is exactly 100 milliliters. I'm going to double check my calculations because I would not like to be incorrect. So 100 milliliters of water. Then what I'm going to do is I am going to real quick. I did make a chart talking about this reaction. We made it as a group. So number one, as you can see, this is going to be the temperature over the time. The time is in seconds and the temperature is in degrees Celsius. I found this handy chart online with an image, and so it's going to be the temperature of the reaction over time. So as you can see, your beginning, you have it good right here. Then the temperature is going to decrease massively when bonds are being broken because they're drawing in some energy, and then you can see right here that it is gradually increasing as bonds are being formed in the solution. So yeah, that'll basically show how the drop in energy means that it is endothermic and is drawing energy in. That is the main conclusion that I want to emphasize from this graph. Yes, so to begin, I have poured my water already, 100 milliliters, into the coffee cup colorimeter. Sorry that you cannot fully see my face. Then I'm going to be beginning with the citric acid. The way you can tell between these two which one is the citric acid is as that they have completely different textures. One is granulated and then the other is very soft and almost like a very fine sand, or you could say like flour. So what you're gonna do here is I'm going to be taking the citric acid and, whoops, dropped that. And I'm going to be putting this in there into the coffee cup calorimeter, exactly 1 teaspoon. And then I'm going to be stirring this pupper around for a little bit. So I'm gonna put that there, cover that up. We wanna make sure that it doesn't necessarily get on the skin, so I'm using the lid. And so I'm going to be swishing it until I believe it has dissolved. And then I'm going to let it sit for approximately 2 to 3 minutes. I will be back once I see that it is 100% dissolved. And then I will add the sodium bicarbonate to the solution, and then you will see the magical explosion of bubbles that will occur beautifully. So I'm just lightly swishing. You don't want to swish too hard and then create splashing, but I have put the top of this over there just to make sure of anything. Since I do have this opened right now, I'm going to move it far away from me since there are hazards associated with the citric acid touching skin. Do remember that it is an irritant. So I'm going to take a pause, continue stirring this until I believe it has dissolved. And then I will be back in approximately 3 minutes. Sorry for all the pauses, but they're very necessary for me to double check everything. Okay, so now it has been around 2 minutes. 2 minutes since and we have the thermometer in here. So what I'm going to be doing next is adding a spoonful of sodium bicarbonate. Don't worry, while we were paused, I did close this, and I'm going to place the contaminated spoon away using the second one. You can never be too careful. So when this happens, I'm going to want you to be up close, and I'm going to close this off so I can properly measure the temperature. What is the temperature right now? It literally doesn't say anything. How am I supposed to know? It's okay. We can figure out how to use the thermometer, Sarah. Maybe 37? Is that a permanent arrow? Wait, let me see what the temperature of my house is. Don't worry. Maybe I should read the instructions for the thermometer. So right now the house is 24 degrees. I'm assuming that the liquid is room temperature. So we are at 24 degrees right now. So I'm going to bring you in closer because I want you to see this so vividly. Now that I've brought you in a little bit closer, I'm going to be taking 1 teaspoon with an uncontaminated spoon of sodium bicarbonate. And I'm going to be chopping this in. My house is currently at 24 degrees Celsius. You can hear the fizzing. And I'm going to take a step back to ensure the fact that no gases irritate my respiratory tract, as I mentioned earlier. I hope that you can hear the fizzing, although I cannot show you due to the system. It is evident that something is occurring in there. I can't see it either, so don't worry. It's supposed to look very similar to a bath bomb, which is what I found when I read up on that they go through the same process. That is where the fizzing of the bath bomb occurs, as well as when you get the fizzy feeling on your tongue from having candy. That is from this process as well, the slight fizzing, but I'm assuming that they use a much smaller quantity because this can be dangerous. I mean, it can lead to death. So these substances individually. So here I get a final temperature of 16 degrees. At the beginning, we started with an initial temperature of 24 degrees, which is room temperature. And this just proves the fact that the reaction was in fact endothermic, as we hypothesized or believed it to be. This reaction was successful despite the fact that the equipment was not always 100% or even 90% effective because we did not have the professional lab equipment to use. After this, the solution will turn back to room temperature gradually, and it will increase in temperature as the reaction has subsided. Thank you very much, Mr. Moa, for watching this lengthy video. We all know that I cannot cut down sentences, and I can only speak in full sentences. So I hope that you enjoyed this, and have a great summer. Thank you very much from Sarah, Lexi, and Kate.